the cost, just the expected cost at time k, no averaging over time, minus its limit, that will typically go to 0 geometrically fast. And you would love to know that rate. And you also like to know this dependency on the initial condition. That's a big topic of research, okay? you know, for complicated models. Yeah. Yeah. All right. So what I'm going to do in the remainder of this lecture. Wow, am I talking super fast? I am. Because I can't believe how far we've gone. Well, anyway, in the remaining 10 minutes, apparently, I'm going to answer 1, 2, and 1 prime. You know, we'll do that by, right now it's 2:35. I guess by 2:40 we'll done with it at the rate I'm going. I don't know. But any questions? All right. Just one caveat. I'll do it for finite state spaces. Okay, so let's just nail it for finite state spaces. In fact, actually, right. What am I saying? We'll do this the whole thing for finite state spaces. You know, everything in one shot. Okay, so I told you I didn't like finite state spaces, in part because you lose topology. You know, there's often a lot of, you know, I mean, yeah, the fact that two states are close to each other far apart is just not reflected in a discrete model. You know, I take x to be equal to 1, 2, ... d, right? So I've got d states. Well, this could be like a queuing network. D is 10 million, and each label corresponds to a point in 10-dimensional space, and I've thrown away topology completely. I've thrown away all intuition. Everything's gone, and so I hate discrete state spaces for that reason. But the insights you get from the finite state space case carries over to the general state space case. So P is a matrix, and it has eigenvectors. And now I need my notes. Okay. All right. So so I'm using x and y or I and j. It doesn't matter. But px, I don't have to put sets in here anymore because I can just look at the probability of going to a point. You know, because it's a discrete. It's probably a mass function. It's not a density. It's just like that. And because it's a matrix, I can talk about eigenvalues and eigenvectors. So I say up to d because it could be repeated eigenvalues, and up to d I can write eigenvectors. Okay, so somebody tell me, I gave you one right eigenvector a moment ago. Give it to me. 1. So we're going to call it lambda 1. It's always 1. And, you know, I can solve PV equals lambda. I'll put a 1 there. I can solve that really easily because I take V1 to be equal to the vector 1, 1, 1, 1, 1. Okay? All right. And remember, I think of functions as being vectors. So this is just a function that's identically 1. Right? And of course, it doesn't have to be all 1s. It could have been all 2s or 3s. But I'm going to take the special case of all 1s. Right? Now, we know that whenever there's a right eigenvector, there's a left eigenvector. And I'm going to call that pi. So this you might not know. So we'll prove this later on. And right now I'll just state it for you. There's a left eigenvector. There might be others, by the way. This is just one. So it might be that the eigenvalue lambda 1 equals 1 is repeated 100 times, and you have 100 right eigenvectors. This is the only one. All right? So we'll figure out ways to rule that out in a moment. And so there's at least one left eigenvector. And in the probability literature, it's always denoted pi. Unfortunately, that conflicts with a lot of the operations research literature where pi refers to a policy. So I apologize, but that's life. Pi in this course is a probability vector. It's a row vector, basically. So what I'm saying here is that the summation over all x of pi of x, p of x to y, equals pi of y. That's what I mean by this. So pi is a row vector. I'm hitting the matrix on the left by pi. But there's going to be others. Could lambda equals 10 be an eigenvalue? Let's see. All right. Well then, p to the nv would be equal to p to the n minus 1v. I'll put it the other way around. If I had an eigenvector at 10, eigenvalue at 10, then I could look at the p to the nth power. That's, it's matrix products times v, and I could go through and do an iteration like this, and you see that you can see a pattern emerging here. Is that if I pull off one p from p to the n, I bring a 10 out front. If I peel off another p, I'll get 100, 10 times 10 out front. And if I keep doing this, I'll get 10 to the n. Yeah, so it's an unstable system, right? But then you have to say, well, what the fuck? This is equal to p to the nv, evaluated at x, is a conditional expectation. All right. So remember what I mean by this? V is a vector. But I'm also going to write v of xn, right? Which is equal to what? It's vi if xn equals I. So that you got to read that to yourself before you go to bed every night as well. We are equating functions and vectors. That's what I mean by this. I mean, I can see why people get scared. All right? But when I write PV, it's a conditional expectation of a function, just like that. And it just turns out that the notation is exactly the same. Matrix vector multiplication is exactly the same as taking a conditional expectation. That's what you've got to internalize that. All right. So we're going to have more homework to practice this. So can anybody imagine that blowing up like 10 to the n? It's bound. It's a finite state space. It can't be. It's less than its max. You know, this. Put absolute value signs around it. It's less than or equal to the max over I of vi. Nah, it's not 10 to the n. All right. So all the eigenvalues are actually in the unit disk. We can't have an unstable system. It wouldn't make any sense. Let's stare at this. So we know we have an eigenvalue here. We could potentially have eigenvalues on the unit disk. That does happen. You know, you could get one at -1, and they can be complex, and they can even be at 0, but they can't be outside. You know. And does anybody remember about Jordan canonical forms? You do. One of you does at least. But when you have one on the unit on the unit disk itself, that tells you a lot about the eigenvector structure. Because you could end up with, like, if you have repeated eigenvalues at 1, there's 2 eigenvectors. Because do you know about what happens with Jordan form? If you don't worry about it.
If they're linearly independent eigenvectors, it's an unstable system.
You'll get instability. Yeah, if you had repeated eigenvalues but only one eigenvector, you get a polynomial explosion. So instead of 10 to the n, you might have n to the k exploding. So anyway, we don't need Jordan canonical form in this course. It's just that you can learn a lot by you can deduce a lot by by knowing that this can't blow up. We can deduce a lot about the eigenvectors of the system. That's what I'm going to say. Okay, cool. So. So what am I going to do? I want to prove an ergodic theorem, and how am I going to do that? Well, so that's lambda 1. Yeah. And this would say be lambda 2, and this would be lambda 2 complex conjugate, because when you have a real matrix, the eigenvalues come in complex conjugate pairs. And let's see. So first I told you that I can't have 10. Well, that's going to screw us as well. So suppose that, so I've got PV equals lambda 2V, and lambda 2 has modulus equal to 1. All right, then I can go through and do the same argument. All right, and so what's going to happen is that this is just saying the expectation of V at time n is equal to lambda 2.
Why'd you square lambda?
Oh, it's not squared. It's not squared. It's just that I don't want to use a subscript because it looks like a vector, an entry of a vector. You know, I'm using a superscript. This is, oh, I used a subscript here. Okay, I'll use subscripts. Yeah, often I'm worried about confusion between entries of vectors and and all that. Let's call it that. No, thank you. Thank you. Good catch. So anyway, so just as before, if PV is lambda 2V, P to the NV is lambda 2 to the NV, right? And P to the NV is nothing but a conditional expectation. It's the same thing, and that is that. And I wrote N. What the hell? And I forgot the N. Cool. So that's not going to converge, right? I've got this lambda to the n, which is just going to go spiraling around the circle. And, you know, the average will converge, right? You know, if I average this thing, the average of this will go to 0, you know. So I can say that. I can say that 1 over n, sum k equals 1 to n minus 1 of p to the k v at x goes to 0 as n goes to infinity. You can show that, that the average of this is 0. You know, I'll leave that to you. But p to the k does not converge. You know, no, that's going to be eta. You know, the eta v if you want. You know, the eta, I've been talking about the mean of this, the steady state mean. All right, so we don't like complex eigenvalues that are on the unit disk. That's bad, because the ergodic theorem I'd like to prove cannot hold. You all see that? Okay, so then here's our assumptions. Oh, no. How do I say this? Let's do this right. Let's do the linear algebra all the way. So the whole problem, when I say repeated eigenvalues, I mean you look at this characteristic function and it has repeated roots, okay? All right, so the first assumption, it's a simple group. There's not a lambda minus 1 squared or lambda minus 1 cubed. It's just a lambda. If I factor, it's just lambda minus 1. All right, and all the other solutions are strictly within the unit disk. Okay, I'll write that lambda 1 equals 1, right? And then I can, without even thinking, prove these ergodic theorems. It's nothing, all right? With a little bit of algebra. So you understand the assumptions. So I'm ruling out these guys on the unit circle, and this is a single eigenvalue at 1. All right? And so the most beautiful way I know to prove like the ergodic theorem is to transform P and move this eigenvalue 1 to 0. To make it really stable. So I'm going to take that eigenvalue 1, I'm going to pick it up, and I'm going to drop it at 0. And how do I do that? I can kill this, right? Yeah.
Subtract off the added product.
Yeah! Where'd you get that? Somebody studied the linear algebra. Cool. Cool. All right, so I'm going to denote P tilde as P minus. I'm going to write some more scary notation. I'm going to use some funky notation for outer product. I don't need to do this, but if I don't, things get even more confusing. Now, this is nothing. Ignore it, okay? 1's a column vector, pi is a row vector. You can multiply a column vector times a row vector and get a matrix, right? But when you write 1 times pi, it starts to look crazy. I just want to make it louder. That's all I'm doing. So this notation is just to remind you, the thing on the left is a column vector, the thing on the right is a row vector, and I'm just doing standard matrix vector-vector multiplication to get a matrix. It's an outer product. Thank you. Okay, so what this does is I'm going to show you this Austin's conjecture here keeps all the eigenvalues intact. It doesn't change anything except take this one guy here and move it to the origin. And let's see that. So first of all, what is p tilde times 1? All right. Well, so it's p1. So again, 1 is just 1, 1, 1, 1, 1. It's a vector of 1s. And then I've got this outer product, which is a matrix times 1. All right? All right. So column vector, row vector, column vector. Multiplication, you can do it in any order you want. So if I take this product first, I get pi.1. I forgot to say pi is normalized. Damn it. Pi is a probability vector. Damn. I think I did say it, but I didn't write it down. So pi is normalized to be a probability vector. So pi 1 is just the sum of the pi k's, which is 1. So so this is p1 is 1 minus 1 times pi dot 1, and pi of 1 is 0, so I get vector 1 minus vector 1, the vector 0, 0, 0, 0, 0, 0. All right, so that's one thing. So we've definitely taken that eigenvalue corresponding to 1 and shifted it to the origin. What about the other eigenvectors? Well, here's an interesting fact. Suppose that PV equals lambda V, and lambda is not equal to 1. All right. What you can do is this. I can look at pi PV. Right? So V is a column vector, P is a matrix, that's a column vector, pi is a row vector. So row vector, column vector, I get a number. All right? So I'm going to do this multiplication first, and I said PV is lambda V. And you see what I mean? Pi v, it can look confusing sometimes. This is an inner product. Pi is a row vector, v is a column vector, so it's a dot product. But I can also do it the other way around. All right, I can multiply pi and p first, and then multiply by v. And we know pi p equals pi. And how is that possible? I got two different answers. Yeah, and so those of you who remember your linear algebra say, well, duh. So how can these be equal? Only if they're both 0, all right? So the right eigenvectors are orthogonal to the left eigenvectors if the eigenvalues are different. That's a linear algebra fact. So pi dot v is 0. And so therefore, remember I was trying to say I'm not changing the other eigenvalues. If I take p tilde and hit it by v, and I'll just do the same thing. Right? I've got p tilde is just p minus this outer product. All right? And then I multiply these guys together first, I get 0. Okay? So if you've taken a good linear algebra course, this is all like old stuff. And if you haven't, you should know this. You know, it's really basic linear algebra that's really useful. Okay. Happy? Questions? No. No. Cool. All right, so let's put this to use. So what basically with this p tilde guy, I've taken this and moved it here, and now all the eigenvalues is strictly within the unit disk. So p tilde at the end goes to 0. You know, I mean, you were supposed to have had like a bit of linear algebra or something. All the eigenvalues now are less than 1. That deserves another color. Okay. All right. So what do you do with this is follows: is that now I can prove my ergodic theorem because I can look at p tilde, say squared, right, which is p tilde times p tilde. I'm going to do the same arguments I've done before. Something nice happens. This is another thing you'd learn in a good linear algebra course, is that once you do this, nice things happen for powers. I'm going to get a p times p, right? And I'm going to get this times this. And then I'm going to get this times this. And then I get this thing squared. Okay. So that's a matrix times a matrix. And you know, one's a column vector, pi is a row vector, one's a column vector. And this is a projection, so it's not surprising it's square. So by definition, it squares 1. You know, pi times 1 is 1. So you just get 1 times pi, right? And p times 1 is 1. That's 1 times pi. And pi times p is pi. That's 1 cross pi. All right. So these three terms are all identical except for the sign. And you get p squared minus 1 cross pi. All right. And so by pattern recognition, or by induction if you like, I can replace the 2 by an n. I can repeat this argument. So that's another beautiful fact. Bring out the colored pen. So that's why the ergodic theorem is so fast when based on linear algebra, because you can actually decompose by doing this, the thing that you care about, which is really that, is equal to something that we know goes to 0 geometrically fast, because all its eigenvalues are less than 1. All right. But let's make sure that's clear. So this goes, I mean, I'll prove it for you in the case of distinct eigenvalues, okay? All right. But the fact that p to the tilde n goes to 0 geometrically fast. Which is exactly what I wanted. Remember I said I want, well, maybe you don't know that. P tilde to the n is this. Is it clear what that is? Let's think about that. Somebody tell me what this is. Somebody who feels insecure. So 1 is 1, 1, 1, 1, 1, 1, 1, and pi is, a vector. All right? So here we're basically taking that row vector pi and just repeating it over and over and over again. So all the rows are the same and equal to pi. So the row index, this is row column, is irrelevant. And y, you're plugging in pi of y. So instead of a QED symbol, put in a happy face. We've proved the ergodic theorem. So, provided we have this eigenvalue structure, we've got an ergodic theorem. So it says that this goes to 0 geometrically fast.
Pi is a row vector, right? Pi of y.
No, I'm just saying I want the probability that xn equals y, given x0 equals x, to go to pi of y as n goes to infinity geometrically fast. And I know that because p to the nx to y is precisely that. Those are the same thing. That's what I mean. Well, so that's a row vector, and that's the Weiss entry. Y goes from 1 to d. Okay? Now, what about the rate of convergence? It can get ugly. I say geometrically fast. What rate? If there's distinct eigenvalues, you can make that very clear. Okay? So, that's all I have to say. They could be complex, except for, of course, lambda 1 equals 1. The first guy is always 1, and all the rest are less than 1. That's the assumption I imposed. Then there's this wonderful spectral representation. I don't know. Have you seen this? Let's see if I can. So this is V lambda. I'll put a tilde. Actually, let's put the tildes in. It's the tilde guy I really care about. That's that's a thing that's the thing that gives me the rate, right? I want to understand p tilde n goes to 0. And so that's a diagonal matrix, and V is a vector of is a matrix of eigenvectors. Well, I mean, it's a spectral representation. There are other names for this. It's what's that? It's a diagonalization. It's a
Decomposition.
what?
Eigendecomposition.
An eigendecomposition. Okay. Anyways, every single area will have its own name for this. But the proof is the other way around. It's really trivial to take it to the other side, take a V inverse over here and a V there, and show the resulting matrix is diagonal. You just do it by, because of the fact that they're distinct eigenvectors, you can do this. And these are linearly independent for reasons that are given over there. Okay, you can actually do that. And then what you can do is if you look at p tilde to the n, which is the thing we care about, you know, you basically, when you multiply p tilde to the n, you multiply these things to the n, and these guys cancel out, you know. And so what you end up getting is the same representation. You know, so basically p tilde to the n has the same eigenvector decomposition because it has the same eigenvectors, and its eigenvalues are just the lambda i's to the nth power. But you can also just see it directly by algebra. Okay? Yep.
So the way to think about this is like we're taking a matrix that isn't nilpotent and we're making it nilpotent. It's like we're multiplying it over and over until it goes to 0. Like that's what that says.
Oh, I don't know. I don't know how to answer that question.
P tilde n goes to 0.
Yeah, it's
You keep multiplying it.
Well, it's never nilpotent, but I mean,
You're saying it approaches 0.
yeah, approaches 0, but it never is 0. So, yeah. I mean, but there are examples where it does. I mean, there are Markov chains where all the eigenvalues are at 0 but 1. So this thing becomes nilpotent, but not. I mean, it's an approximation. You know. No, but it's just this. I mean, p tilde to the n is just this, and so you can see then we know the way to convergence. Then we know that p tilde. Well, the thing that we really care about, which is this. It's going to be given, if you know, basically, I don't know what the hell this is, but I know the thing that depends on n is really simple. I've got lambda 2 to the n, lambda 3 to the n, lambda 4 to the n. So it's sum k equals 2 up to d of some coefficient, I don't care what it is, x, y. I mean, maybe I do in some applications, times lambda k to the value n. You know, and that goes to 0 at rate lambda 2.